Hi all, welcome to another session from Narrow Research. I'm Srijit here. So in this session, I will be continuing the applications of machine learning potentials, which we have started the discussion in the last session. So here, I'm focusing today about the ionic diffusion in solids. So actually, it can be understood as a sequence of thermally activated pops of mobile ions such as lithium or sodium between energetically favorable sites in a crystalline or amorphous lattice. So in AMS, combining machine learning potentials with NEB method provides a powerful and efficient framework to study this process. So MLPs reproduce the density functional theory potential analysis with high fidelity while being computationally inexpensive, making them ideal for exploring diffusion mechanisms in large supercells that are representative of real solid state materials. So actually, I have already given a session on NEB, the intro session, that what are the things to be taken care. And also I have briefed the same concept in one of our webinars, which is available in our LMS platform known as narrow.graphy.com. So I'm not briefing those concepts here again because I have already taken it. So here I'm just focusing on a step-by-step methodologies, that what are the things which we have focused here in this, this typical case. So in the first step of this approach is the construction of the reliable diffusion endpoints. A periodic solid structure is optimized using a DFT engine such as BAND. But generally it is a little bit complicated, but we have already done the optimization covering up the lattice. And sufficiently large supercell is created to avoid artificial interactions between periodic images. So ionic diffusion is typically vacancy or interstitial mediated. So defects are introduced accordingly. So the fully relaxed initial and final states are then defined by placing the mobile ions in the neighboring stable states, ensuring that both structures corresponds to local energy minima under the fixed lattice parameter. So you can see this is the initial structure. And if I go to the next structure, you can see the final structure. So these are the two structures which I have taken for this NEB. And you can see that what are the inputs which I have set here. The maximum number of iterations is 100, number of images is 90. The initial system, final system, everything. And this typical intermediate. So we need to optimize the reactants and product here to get the final, state. I mean the final concept of ionic migration here in this interface. And also the other details I have set as default. And this the NEP method is used to connect these two endpoints by a chain of intermediate images that approximate the minimum energy path for ionic migration. So in AMS, these images are generated by interpolation and optimized simultaneously with the spring forces maintaining the continuity along the path, while true forces drive each image towards the lowest energy configuration perpendicular to the path. So the use of climbing image NEB or CI NEB is particularly important as it refines the highest energy image to accurately locate the transition state and thus the migration barrier. So this is actually the concept which I have just briefed. So by employing this an MLP as a force field for NEB, the computational cost is reduced by orders of magnitude compared to DFT NEB without sacrificing essential accuracy. So this allows the use of larger supercells, better lattice relaxation around the migrating ion, and systematic exploration of multiple diffusion pathways. So crucially, the MLP must be trained on DFT data that include not only equilibrium structure but also distorted and transition state-like configurations, ensuring reliable forces along the entire diffusion path. So actually, I have already briefed this concept of how to locate a transition state in an organic reaction in one of the examples which I have briefed earlier. So you can refer those videos also, which is available in our channel. So the migration barrier obtained from MLP NEB corresponds to the activation energy for a single ionic pop and provides microscopic insight into the diffusion bottlenecks, coordination changes, and lattice distortions. So these barriers can be directly compared with the benchmark of PFT and NEB calculations for selected pathways to validate the MLP. Once validated, the barriers serve as inputs for transition state theory for kinetic models linking atomistic mechanisms and to microscopic transport properties. So finally, NAB-derived activation energies complement long timescale MLP-based molecular dynamics simulations, while MLP-MD yields temperature-dependent diffusion coefficients from mean square displacement, which explains why diffusion occurs at a given rate by identifying the controlling energy values. Together, this integrated MLP NAB MD strategy in AMS, it provides a complete physically grounded description of ionic diffusion in solid, particularly well suited for battery electrodes and solid electrolytes. So these are some of the concepts which I would like to bring. Now let me show you that what could be the expected outcome of this step. So let me go to the animation, and I will show you that how this this diffusion or that calculation can be taken care here. So let me show you that. So this is actually the output. So you can see that migration on the left side from one point to another, the slow migration. So this is actually the methodology which we can brief using NEB methodology in with ML. So let me finish this session, and we can see in the next video with another case study. Hope you can refer the basics and the inputs of these calculations in our LMS platform, as well as in our a video related to NEB, the basic video that what are the things to be taken care. Okay, thank you.